Okay, good morning, everyone. So today we have Professor Defan Zhou to give us a talk. And so this is a regular HKU IDS seminar series. And it's given by our professor, Professor Defan Zhou. He is an assistant professor at HKU IDS. And Professor Zhou will be delivering a lecture on unlocking interpretable control for large language model and beyond by Sparse Autoencoder. And Professor Zhou is assistant professor in HKU IDS and computer science, also CDS jointly. Yeah. And got PhD in computer science.
I guess no need to introduce that. Everybody from ideas.
Okay. Yes. Actually, I'm a little bit surprised you got a bachelor degree in physics. Yeah. Okay. Anyway, so yeah, let's welcome Defan to give us a talk.
So yes, thanks for introduction and thank you guys for coming to the lecture. Okay, so as just Professor Lee mentioned, I was studying physics. So actually this talk here is also something like the physics of large language models. So let me also talk about my background. So I previously was working a lot of things about theoretical stuff. So theoretical kind of stuff, if you take my course, okay, you will see a lot of proofs. But as a presenter, introducing proof is pretty difficult. And also, even for the large language models, I guess nobody really cares about proofs. As the most of the thing, you really cannot have a very precise theory plus at a very rigorous theoretical proofs. So later, so people just come to study the large language model from the mathematical perspective, like building very rigorous theory to the physical perspective. Like people can just propose some hypothesis and try to discover some phenomena and then try to build some tools to get some empirical but also consistent understanding of what happens in the large language models. So this just also the intuition of this work. And also, this is just a kind of joint work with some of my fantastic students and collaborators. Okay, so let me first introduce the basic thing about the interpretability of large language model. So the background is very clear. So I guess everybody is using large language model now, and everybody knows that large language models can do much many jobs pretty well. But yeah, definitely just like you, I use large language models more than understanding large language models. That is definitely true. The former is easy, the later is super difficult. But there must be some people need to do that. And also there's a group of people, especially they just also have some applications of the interpretability of large language models in certain domains that who really cares about understanding, who really cares about why the large language models can give you such options and decisions. Okay, so, but the problem is pretty difficult as the large language model is not like the conventional machine learning case where we just have a bunch of features and we just, using the standard kernel method, linear method, or just the neural network method. But the large language model, people just build using the large language model is primarily built based on scaling law. People just try to make the model larger and larger using more data set, just can hope that the power model can learn a lot of, can learn more intelligent stuff from a massive data set. Okay, so given that we have billions of parameters, we are pretty difficult to understand what is the model know and how it processes information. And also, there's just many safety critical applications really need some transparency, like if you're using large language model to help you to buy stocks, and sometimes it just costs a lot of money loss. You need to understand why it happens. Okay, so the goal of interpretability, there are two sides. The first one is the understanding. Okay, we first understand the inherent working mechanism of large language models and understand why it happens. And the second one is that what if we have the understanding of the interpretability of large language models, how to leverage that to make the model become better, how to make the model behavior more controllable, to really to understand, to try to follow our first principle to add it to the model to satisfy our certain requirement. Okay, so yeah, so this is just just a prompt large language model to mention, okay, what can we do by using interpretability? So there are just some conclusions given by both me and large language models. Okay, so from a theoretical perspective, is that we can just try to know the limit of a large language model in handling various tasks. Everybody knows large language model is super powerful, but definitely there must be many jobs that cannot be fundamentally solved by large language models, and we need to know the limit. And then we can push the limit to build a better model. And also we need to understand the failure case, why the failure case happens in the experiment, so that we can more efficiently to find out the next step to work on. It saves a lot of time. And also, there's just some about a safety issue, and we need to make the large language model output align with the anticipate and become safer. So there's just a huge gap between the model in China and the model in the US. Like Anthropic, they're just the company who really advocate the safety of the large language model to make the large language become super controllable. But in China, most of the model, they're just try to shoot for the better performance. So I have heard from my student, they're just, even for Q1 model, they're just a safety team, they only have 4 people. Okay, they are not very care about the safety, but just try to shoot for performance. But I believe that in the later, if the performance has already reached certain level, perhaps the next step is to really make the output of a large language model become reliable, safe, and align with the humans anticipate. Okay, so then if we have the interpretability, we can certainly to provide some interpretable guidance to revise the large language model during the training and the inference to really make them be more aligned with the human anticipate. And also, if we find out what is the most important part, what is the most important neuron of the large language model for certain tasks, we can definitely to develop a more lightweight method to adjust the large language model's output. Just a similar idea as MOE, but if we have the interpretability, we can just perhaps do the similar idea of MOE in a more careful way. Okay, so this is just the interpretability research, interpretability study that has already been approached in multiple perspectives. Okay, so this is just summarized by me. From the very left-hand side, that is just theoretical study. So this is definitely the first attempt that the theoretical people want to work on. We have a bunch of standard theoretical tools that we learn from the textbook. We learn from the very conventional machine learning. We can study the expressiveness, we can study training dynamic, we can study the generalization error. So we can then leverage that kind of theoretical tools to study the property of large language models. And then later, people find out the limitation of the theoretical study because these tools has been demonstrated to be useful for conventional models. But if we really need to make that for very complicated models, the bound, if in theoretical perspective, that is just theoretical bound, is really loose. It cannot help understand to give a very precise understanding of what happens in practice. And later on, people just try to find another cutting point. Okay, they just say, if we really want to understand a large language model, we first need to summarize some key phenomena. So the second part is phenomenon-driven theory. People first develop the well-controlled physical experiments, and then people just do a lot of observation, and then people can say, okay, this observation can be generalized to multiple models, multiple tasks. So, okay, so this is a very nice observation. And then we just specifically build a theory for this particular observation or a bunch of observations. And we then hope that because this theory already have the power to explain certain observations, perhaps it can also be generalized to other observations, which is closer to what happens in practice. Okay, so, and then, why there is, so this is Zoom? Okay. So the next part is empirical study. Okay, so what if we just want to get observations? We can definitely just do more in-depth experiments to understand the observations. And also by doing a lot of observations, we can also summarize like a very clean relationship between some key parameters. Like people can develop like the scaling laws, people can do the representation engineering, people can just look at a lot of attention maps to try to collect some useful information from these observations empirically. But now I think there's just a bunch of other type of interpretability analysis called the general interpretability tools. So the empirical study, the phenomenon-driven theory, you first need to have the observation for certain tasks, and then you can develop the theory for that. But for different problems, you really need to have a different methodology, different roadmap to think about this problem. So later, people just think about that. Okay, can we just have a certain general way that can handle all possible phenomena, all possible things that we need to understand? So this is just called general interpretability tools. Like perhaps we can just build these tools by using training, and we have this tool. We can just using this tool with some slight modification to understand a bunch of diverse phenomena or some diverse interesting things that we want to understand. So this is just the general interpretability tools. The first one is circuit, so which is just a minimal combination of the neurons in transformer that are in charge of certain tasks. So this is just kind of the compression of the neural network architecture. Okay, so we have billions of neurons, billions of parameters. But when working on certain particular tasks, there are just only a few of them. They are in charge of this task. Okay, so the goal of that is just to identify the key neurons and to try to build the smallest circuit that can give you almost 90% of the performances before. And then because we will finally only working on, for example, 1% of the total neurons. So perhaps all the neurons in that small circuit can be super important, and we can just try to find out, do some manipulation of these neurons to understand, okay, to save the computation, something like that. And the next one, the sparse autoencoder. And I remember in my lecture yesterday, there are just already two students or three students. They are trying to give some presentation about a sparse autoencoder. Okay, so a sparse autoencoder is not working on the architecture of the transformer, but working on the representation space of the transformer. Like we have many hidden layers, and we only just try to look at the representations generated by certain hidden layer, and we just try to build some model based on the representations in that layer and do some manipulation on that. So this is just the diagram. Okay, for a certain embedding layer, which people can train the sparse autoencoder to map the representation to much higher space with some sparsity control, which I will introduce later. And try to, because of sparsity control, and the people hope that these the activations or the features in this high dimensional space, they will have a separate concept, and so that we can just easily identify and control the concept separately. Okay, so generally this tool is kind of developed based on the rigorous calculation procedure, and because they are not task dependent, they can just use for general tasks as long as definitely, especially for sparse autoencoder, we can just put out using a very diverse data set and just try to train this sparse autoencoder, and so that if we want to work on certain tasks, we can just leverage that because that already has the information for various tasks. Okay, so in this talk, I will just primarily to discuss our recent work about the sparse autoencoder. Okay, so here just a basic introduction of sparse autoencoder. The idea is pretty simple. So X is just the embedding a certain layer. And the goal is that we know what happens about this representation is that it's just a very dense composition of a multiple concepts together with some nonlinear combination together. So, and the goal is that we want to separate the concept to be some separate features or separate neurons. So the idea is just to leverage the very conventional autoencoder concept, we just have some nonlinear mapping to very higher dimensions, okay? And we have a decoder to ensure that we can map the higher dimensional embedding back to the original space. And we hope that after decoder, we have a very good reconstruction. Okay, and in these hidden features, because we want to separate them, so the basic idea is that for every input, so we just want to identify a very small number of neurons to represent these particular data. Okay, so and mathematically, this just we can just simply to add some sparsity control for the hidden embeddings. So because if for every, so this is just like a dictionary learning. If we just can say every data, they can just using like a few queries to the dictionary, we are done. Okay, we can just say, and the dictionary, which is just the encoder part, decoder part, will every feature in this decoder will corresponding to every item in that dictionary. So they are separated. So we can leverage that to do very precise control. So this idea is pretty simple. We're just using like a very simple no linear network, but definitely you can use the multiple layers, but nobody do that. Everybody just using one single layer to do transformation. And the decoder is just a linear combination. And the training is just a reconstruction plus sparsity control. So this is just why it's called sparse autoencoder. And there definitely have some like engineering tricks to have the sparsity control. People can just, because we just want to control this one to be sparse, okay? So first, the very simple case, is which means that many items of D will be 0. So definitely the simplest idea is just to make sigma to be ReLU. It already cut off a lot of neurons. So that can give you like sparsity, and we can also use top K, like we just do the ranking of the strengths of every embedding, and we just choose top K, and we can also do the best top K, which is just like an extension of top K, and we can just also use jump ReLU, get just different ways to push a continuous variable to 0 and some positive values. So there's just a very key hyperparameter measure called the sparsity, and the people will handle that, okay, which is the average number of active features per input. So definitely, if we allow L0 to be large, which this definitely will help reconstruction because we allow each data to have more neurons to do reconstruction. That can definitely help reconstruction. So, but lower L0 can just improve interpretability because we can better pin down the data to be a combination of several important features. But higher L0 will lead to better reconstruction, but potentially less interpretability. So, but this one is just a hyperparameter, and people need to tune about that. Like this is just a pretty simple, people just tune lambda to try to tune the sparsity of these hidden states. Okay, so the next simple question is that, okay, if we have already trained this SAE, how to use that? So the fundamental usage of SAE is to do interpretability. We can do the feature identification. Because we have the decoder, we train a dictionary. We can just have the concept understanding for each features in this dictionary. Okay, we can understand what the concept does each feature represent. We can also do the mechanism analysis, like if we want to work on this particular task, like which concept, which feature will contribute most to this particular task, we can do this kind of thing about interpretability. And the second one is just called representation steering. Okay, we can just if we find out that some concept is very important to this task, and rather than tuning the parameter, the ways of the neural network, we can just simply do the representation steering. Like this just original embedding, and we just using the dictionary to find out the features that correspond to this particular task, and we just add some to this vector addition, try to strengthen that particular concept that has been demonstrated to be super useful. And also, rather than just simply to use the steering, we can also use the feature space to guide the editing of the model's parameters. Like if we can also try to say, if we find out concept they are pretty important to this particular task, and some other concept they are irrelevant, but if we just want to strengthen this task without changing the performance for other features, we can just using these features to form a regularization term and to add that to the fine-tuning objective functions for this particular task. So there are just many different utilizations of the sparse autoencoder for the task-specific improvement. Okay, so in the central question of this talk, I will try to say I will just first try to study the connection between the interpretability and the steering ability, or just we call that this utility, because we use sparse autoencoder to really to improve the performance. So we call that a utility. And also we just try to say study one thing beyond. Like currently the SAE, they are just working on the standard autoregressive large language models, and recently there's just another kind of large language model called diffusion language models. We also work on that to see whether this kind of interpretability tools can also be useful and effective for the non-autoregressive large language models. So, okay, so here just an example of a representation steering in large language models. So the idea is just we collect a few samples for certain tasks, and we find out we just calculate the steering vector for in the SAE space, and we just do this linear perturbation, and then we hope that the output can satisfy our can match our anticipate. So here just a simple example, like the question is just could you tell what is your favorite food, and also we hope the large language model can give something like about a cake. So cake is just one concept, and we can then just find out the features of the sparse autoencoder corresponding to the cake. And if we do not do the steering, okay, the output just my favorite is mango, blah, blah, blah. But after steering, okay, the output can be something closer to cake. Like I'd say I like cake, it's sweet and festive, blah, blah, blah. So this is just one simple example about steering. We can just inject the certain concept to the large language model to make the output become what we hope. Okay, so the roadmap of this talk is first we would like to do some fundamental analysis. Okay, so these just very fundamental questions, like people build SAE because they hope that SAE can give you some higher interpretability. There are other kind of people, they are trying to say, okay, you already have the SAE, can we just use that to improve our tasks? We call that utility. But nobody just try to really build connections between the interpretability and utility. So this natural question says that, okay, if we have a better SAE, which is more interpretable, can we just, must give you like a better utility for the downstream task? So we first do that kind of analysis. So the second one is that we try to build SAE for non-autoregressive large language model to see whether this kind of tool is really general, whatever this training paradigm is, whatever the architecture is. Oh, sorry, the architecture they are the same, only the training and the inference paradigm, they're different. Okay, so so this is just a gap between the interpretability and utility, like a bunch of people just try to develop SAE for finding interpretable features, and there's just a bunch of people, they try to steer the critical features for concept injection and characterize the performance of the steered model. So, and the community assumption is that people generally, in our mind, we definitely try to believe a more interpretable SAE can produce more useful features for downstream tasks. But that is true. Okay, so there's just no prior systematic study, and there's just a lack of the very detailed study about, okay, care about the different architecture, different sparsity level, and also they just already have some benchmarks about the interpretability of SAE and the benchmarks of SAE utility, but nobody try to connect them. So the goal of our analysis is just we try to build some statistical evaluation about the causal relation. Or I cannot say that is causal relation, but just the association relationship between the interpretability and utility, and to have some deeper analysis. So this just like the measurement about interpretability and steering. So I have to say, this criteria is not rigorous. So about interpretability, so definitely nobody really have the mathematical rigorously way to characterize interpretability. So generally, what people do is just, okay, people just use some data and collect the output, and then using another large language model to say whether this output is really match the concept of that particular feature. So the interpretability process is done by the large language models. Okay, using large language model to analyze the output and the input, whether they have some like a relationship. So steering utility can kind of be more rigorous because we just manipulate the steering vector and we can have the final performance, but there's still like a combination of different steering scores. Some of them, they are still be done by be judged by large language model. Sometimes it can be done by using some mathematical calculation, like a perplexity, some kind of calculation like that. Okay, so our evaluation is just pretty straightforward. What if we want to do the statistical analysis about the association relationship between the utility and the and the interpretability? So the idea is just we need to collect many different SAEs, trying to use in different ways, trying to use in different backbones, and then we just make a pair about for each SAE. We can just calculate its interpretability score and the utility score, and we do the like a pairwise association analysis. So like for each SAE, we can just have the interpretability score and we have the steering score. And we train like 90 SAEs using different architecture and the sparses to do the pairwise analysis. So you may be asked, okay, why we only train 90 SAEs? Because training one SAE already costs a lot of GPU. So training 90 SAE already takes about several weeks using 8 GPUs. Okay. But we believe that it can already give some like statistical results. So for the pairwise analysis, the idea is just to use the Kendall's rank coefficient, and we just consider 2 SAEs, and we define the concordance indicator, like we take 2 signs and putting them together. So the idea is just the idea is pretty simple. So which one SAE has the better has a higher interpretative score, and it also has a utility score. This one will be 1. But if they have the higher interpretative score but the lower utility score, this one will be -1. Okay, so this is just a kind of taking the sign and then calculate the correlation. You can understand like that. And finally, we can derive this coefficient, and this coefficient will definitely from the -1 to 1, and if it is very positive, which means that we can very confident to say higher interpretability can give you higher utility. But if this is negative, we can only say, okay, we can say interpretability will give you worse utility. And if that is closer to 0, we can say, okay, perhaps they are not very correlated. So let's see what is the outcome. When calculating, okay, definitely the outcome is, luckily, that is not negative. It is still positive, which means that higher interpretability can still give you like kind of a good utility, but they are just a kind of weak positive. So the correlation is far from strong. Like when doing this, before doing this experiment, we anticipate that that should be like 0.6, 0.7 like that. But the problem is just like a 0.29 or just a 0.3. Okay, so we also do this kind of different way, but the top K can give like a higher correlation, but ReLU is kind of not very good. Okay, so this just like a very brief like statistical result about the correlation between the utility and the interpretability. So, but the next question is that, okay, when people are doing the utility, so this one, when we are calculating the utility, we use all the features. We use all the features discovered by SAE. That is not a very good idea because different features, they have different utility. They have different steering ability. So when people are really using steering, using the SAE features to the steering, people only use the features that can give you like large improvements. So then we just try to consider one may selectively find the features that are good at the steering. Okay, we will no longer only care about all the features. That will, some features, they only give marginal improvement, so that will cause a lot of statistical noise. Okay, so this just comes to another part. It's just we want to make our work become like a stronger. So we also consider another problem. So if we do not know, if we do not have the test data, okay, how to find the feature, how to really identify the feature that is very good at steering. Okay, so so we just propose another like criteria called delta token confidence. Like we just testify all the features and do some perturbation along that features. And with then we characterize how the feature perturbation affect the distribution of the token sampling, because we know that large language model is a probabilistic model. If we manipulate this particular feature, the output token distribution will be altered, and we just try to find the features that can affect the distribution of the next token sampling a lot. Okay, so this is called a delta token confidence. If this delta is large, we can say, okay, this feature perhaps can give you a better perturbation on the output of the large language models, which could be possibly better for steering. Okay, so first let's see what is performance of our new criteria. So there are just already some work there try to work on these particular problems. So the first one is called SAE-based. SAE-based is just we randomly to pick the steering. Okay, we use all the features to the steering and we calculate the average. And there's another previous work, they just try to develop some called output scores to select the features for that is good at steering. And this is our work. Okay, so definitely we can see our work has a much better performance compared to the baselines, especially for these two. Okay, which means that our method can kind of give a be better for finding the features that is better for doing the steering. Okay, and then let's see what happens if we only care about these features. So previously we hoped that, okay, because people just using this feature for steering, so if the higher interpretability, if the SAE is higher, is better interpretable, we hope that we can be better to use for the steering. But here is the result. The result is also surprising. This correlation become even weaker. Okay, so this is just all the features. We still have kind of the correlation, but we only hear about the high utility features. This association, this relation become even weaker. So we kind of have some like hypothesis about that, and we are still working on that. Perhaps this is we kind of conjecture this could be the potential issue of the interpretability, because the features with the stronger utility could be easier to be discovered. Okay, so like even the model interpretability is not very good. The strong utility, the high utility features could still be clearly discovered. So in that case, if you only care about the high utility features, there will be no associations. So the difference about this, like the SAE with better interpretability or worse interpretability, could be largely affected by the low utility features. Okay, because the kind of high utility features there can be equally discovered by even your SAE is not trained well, you can still discover this kind of strong features. And the other things we conjecture is that based on our understanding about finding the high utility features, the utility feature is kind of corresponding to how the model's output can be affected by the perturbation of this feature, which is just like the first order information of the feature. But for SAE, we only care about zeroth order. We only do the reconstruction. We have no regularization, or we have no knowledge about the first order information. So one of our future idea, perhaps when we are training the SAE, if we hope that this idea can provide as more utility features as possible, perhaps when training the SAE, we can also have some regularization about the first order information to push some features can have a higher effect on the model's output. So this is just kind of the future work. Okay, but this also suggests that even if SAE is not optimized for interpretability, but if we only care about certain features for utilization for utility in the downstream task, that is still useful. It still learns features can still be valuable for the downstream task. So this is a good idea. Even though your SAE is not trained very well, you can still identify some strong features that is good for the downstream task. Okay, so yeah, this is just the first part of this lecture. So any questions so far? Okay, so yeah, perhaps we can just keep all the questions later. Let me just finish the second part. So second part just kind of separate. So we are just to try to say, because SAE has already been widely applied for autoregressive large language model, they're already like pre-trained pre-trained SAE models for different architecture, like Q1 model, Llama. So nobody is using Llama now. Okay, and also there are just some models trained for Gemma model. Okay, but recently, especially for last year, we already observed the widespread development for the diffusion language model. Okay, so some people believe that it's just a promising alternative for text understanding and generation because it can provide multi-token prediction for each step. So finally, it could give you accelerations, can help to make the inference become faster. Okay, and it can sometimes have a favorable scaling behavior. So the natural idea is just, okay, a lot of people they have demonstrated SAE to be useful for autoregressive large language model, and we just try to say, okay, if the diffusion language model is the future, okay, or just the primary is the important part of the future, perhaps the necessary thing we need to do is to also build these interpretability tools for diffusion language model, and we need to take a first step to see what happens, what is challenging, and whether SAE is also useful for diffusion language models. Okay, so the naive idea is just, okay, we believe SAE can be directly applied to diffusion language models because they have the similar backbone. So the architecture or the model can be directly transferred from the autoregressive large language models to the diffusion large language models because they are just using the same architecture. Even for the diffusion language model, like the Dream diffusion language model, they are just directly adapted from the Q1 architecture. Okay, but if we think of that in a deeper way, so this is just really not a plug and play tool because the diffusion language model has fundamentally different in terms of the training and the inference because sparse autoencoder is still need to be trained, okay? And because of diffusion language model, they have different training and inference. Perhaps when training the SAE and use the SAE for steering, we also need to have different options, different ways. So large language model, the good thing for large language model is that it has very a fixed causal mask to collect activation from fully observed prefix. But diffusion language model, okay, we just have the random. We are random correction level, and we just try to we look at the partially masked sequence, and we want to predict some masked tokens. So these are just the difference in terms of the training. And the large language models, okay, the inference for the large language model is also fixed from the left to right to always to the next token prediction. So the paradigm for the steering is fixed. But diffusion language models, they just try to use denoising. They just try to unmask some masked tokens one by one or just two by two, something like that. But you have no idea about which token will be unmasked in the next step as long as before you compute before running the model. Okay. So this also makes the inference part of the diffusion language model more complicated, and we also need to think about how to develop the SAE steering to adapt to that particular inference procedure of diffusion language models. Okay, so generally, so because we just try to do the first attempt, so we allow all possible choices and do some examinations. So for the training, we just consider multiple different training things. So first, we can just train the SAE based on the embeddings of the master tokens. Okay, we only care about the master tokens and use that embedding for building the SAE. And we can also use the embeddings of the unmasked tokens, but definitely we can just putting them together. So this is just a very easy thing to do. Why we have this understanding? Because the left one is actually simulated the same training strategy of diffusion language models, which leverage all possible information and only try to predict the masked tokens rather than all the tokens, rather than next token. So the first one is kind of a thing that match the training trajectory, a training strategy of diffusion language model. The second one, you can regard that as a complementary to the first one. And the steering is still similar, but the steering just, we have, for large language model, we only need to do the steering for one single next token prediction. But for diffusion language models, we have no idea about which token will be predicted in the next step. So we need to consider, perhaps we need to add the steering for all the embeddings of all the tokens. Okay, but we have this control. This one will control which token will be activated for doing the future steering. So we also have two ideas. First one is just we do this steering for all the token embeddings. And the second one is we first try to find out which token will be predicted in the next time. And then we just do this steering for these particular tokens. Okay, so next is just some experimental result. So we have a bunch of questions, okay? We just can try to understand the property, the performance of SAE for diffusion language model from multiple perspectives. So first one is to see whether, the standard one, first one is to see whether SAE can really provide interpretable features. Okay, so the evaluation is just the reconstruction fidelity and the functional fidelity to see whether the SAE can be successfully trained to help do the reconstruction and it does not affect the performance of large language models. The second one is reconstruction, and the second one is to hope that it will not affect the large language models. Like we just replace some particular embeddings by using SAE, and we see whether the training loss, the cross-entropy loss of the language model, whether that one will be heard, whether that one will still be kind of at a reasonable level. So here is just the result. So we also have some comparison with the large language models here. So the first one is called the delta large language. So we first look at the second one. So the second one is very easy to understand, just the reconstruction loss. So definitely, because we are working on the embedding, so whatever the embedding is, as long as the ReLU and the autoencoder, it works, we can definitely do the reconstruction. So this one is very easy to understand. Even for the diffusion language model, the reconstruction can also be quite good, especially when we have a higher sparsity. But the surprising thing we find out is the large language model, the language model loss, which is the cross-entropy loss, after replacing one particular layer embedding to our sparse autoencoder. So for the language model, if we replace that, you definitely have some information loss. Okay, so finally, you will have the positive gap. Like when you are replacing the particular layer by the sparse autoencoder, you will have a worse language model loss function. But this is kind of different for diffusion language model. Like in the lower layer, this is just the first layer. If we just replace that layer by the sparse autoencoder, we can even get the improvement of the language model's loss function, which means that the perplexity generated by the large language model, they are even smaller. So one of our conjectures is that because like previously the language model, they are just when training SAE, they are the same as the training of large language model by only looking at the next token. But for the diffusion language model, we are trying to use both unmasked token and the masked token together. Perhaps using the diffusion language model, using the SAE for diffusion language model, we can see all the token information before training the diffusion language model. Okay, when training diffusion language model, we only try to predict the masked token. But for using SAE, we see both masked token and unmasked token. Perhaps that can provide additional information so that the final loss function could be smaller. So this is just one surprising thing we identified for using SAE for diffusion language models. And also then we can do similar thing to see whether the SAE features can enable effective steering. So we also have some like a bunch of the criteria. So C is whether the concept is well aligned, and we hope that it can be as large as possible. And the P is that because sometimes we do the steering, the output sentence will be kind of weird if you push too much about the steering. So we just care about whether this output sentence is not more confusing, like the difference between the perplexity of the output sentence before the steering and after steering. So generally, this one will be the negative one, and we hope that it can be positive. We hope that it can be closer to 0 or even positive. If that one is positive, which means that after steering, the output sentence is even better. Okay, but that is kind of hard. So, but we can only care about that. So generally, we find out that on average, the steering ability of the diffusion language model is kind of better than a standard language model. So this also kind of match some like early observation, just early observation in the first half year 2025. This is just one paper saying that, okay, the diffusion language model has a better embedding space, but I don't know the details about that paper, but they also have the similar argument. So this just like kind of the validation of that argument. Like, yeah, if we do the steering on the embedding space using SAE for diffusion language model, we can get a better concept injection performance and also the smaller degradation of the perplexity of the output sentence, which means that, okay, the SAE feature is definitely effective for steering, and also it can provide better steering performance. And then we also try to do some early attempt to see what can we do by leveraging Sparse Autoencoder for some task that's specifically tailored to diffusion language model. So I asked some expert working on diffusion language model. They told me that, okay, the most fundamental issue for diffusion language model is that how to define the decoding order, because we can just randomly to find the order, or we can just have some like a principle or criteria to decide which token can be decoded in the next step. So if we only decode the next token along the order of the sentence, that will be exactly the autoregressive large language model. But for diffusion language model, they definitely don't hope that, but they can still try to have some like a rough principle to guide the order of the decoding. So they're just already a lot of people they're working on that. So the original one is just to match the theoretical thing. They just theoretical says that you can just randomly pick one token to unmask. But definitely, if people do that kind of experiment, they find out the performance is pretty bad. But and then later, people can say that, okay, you only try to find the most confident token to predict in the next step. Okay, about the confidence, people can just use in top K margin or just the entropy. Entropy is just a less uncertain token. Like we just always try to predict the token with less uncertainty, that is less uncertainty, that is has a higher confidence to predict that next token in the current step. So, and this one can give you much higher accuracy, like 56% and 59%, okay? So this means that the decoding order is really important for diffusion language models. And we just hope that whether we can use a sparse autoencoder to really identify some like feature dynamics according different decoding strategies. So, and because of time limit for this work, we only do some simple things. We just propose two criteria. The first one is called pre-mask stability. Like we just collect the tokens that hasn't been unmasked during the inference. And we see after each step, what is the change of the SAE features for that particular token. And we, for example, for mathematically, we just calculate the similarity of the SAE features for that token in the subsequent two update. And we only care about the unmasked token. And we find out that, okay, the similarity of the random order things, they're always high, which means that the similarity is always very large at every unmasked iteration. And for the entropy and the top margin decoding order, in the beginning, this similarity is becoming higher and higher. But even in the beginning, okay, this similarity is lower, which means that it has received a larger progress during this decoding order. Okay, so this kind of says that if we're using this kind of better decoding strategies, like the similarity is lower, the more progress are made to the masked tokens during the decoding. But if you only use a random order, the progress is smaller. And we also look at what happens after the decoding, what we call post-decoding drift. Like if the token has already been decoded, what happens if we decode the further tokens, what happens? What is future changes for that particular decoded tokens? And similarly, we here it's kind of not using the similarity, but we use 1 minus similarity. Okay, for the random order, you can see this just always keep lower level, which means that always the progress made on the unmasked token or even the decoded token, they are just kind of smaller. But for the other decoding strategy, sometimes it is just higher, which means that we are still making the progress on the tokens, even the tokens has already been decoded. So we are not saying that this can readily to provide some like a methodology for building better decoding orders, but based on the SAE features, we can already identify the difference between different decoding orders, and we can, for example, have some higher level understanding saying that, okay, if you want to build a better decoding order, which kind of thing is necessary? We can at least have that kind of understanding. And later, we just try to say, sometimes people using SAE to design better post-training method, to define best fine-tuning method. Okay, and this definitely requires that the SAE can be changed a lot during the fine-tuning, during the post-training. So we just want to characterize the stability of SAE during the fine-tuning. And luckily, there's just some open source SAE open source diffusion language models and open source checkpoints on Hugging Face. So we can already leverage that. And we just try to compare the performance between, we just using the SAE of the base model and to evaluate its performance on the model after SFT. And luckily, we just try to find out, okay, they are pretty stable, like the loss, this explained variance is very large, and the delta loss is also pretty good. And also, for some lower layer, we can also get better language model loss functions. So this shows that even after fine-tuning, okay, the SAE built based on the base model can still be stable, and so that perhaps some key features will be maintained during the fine-tuning of the diffusion language model, so that we can, this also suggests that perhaps we can further develop the better fine-tuning method based on the information from SAE. Okay, so that is just all the content, and here we have some like summary and takeaway. So the summary is pretty straightforward, and we discussed the interpretability and the utility of the current SAE. They are not very well consistent, but with better feature selection, SAE can still provide a good steering ability, even though the interpretability of that SAE is not very good. And also, we showed that SAE can be successfully used for the mechanism interpretability beyond the autoregressive large language model, and it can be useful for diffusion language model. And we have some very positive initial observations for using the SAE as a guidance for diffusion language models. And we have some future directions. First, there are just two ways. The first one is saying that, okay, whether this SAE can be trained better, in a better way, like what we have mentioned before. If we just really want to connect the utility and the interpretability of the SAE, perhaps we need to have some first order information, putting that into the training loss function of the sparse autoencoder models. Not only focusing on the reconstruction and the sparsity, we need to add some first order information as a loss function, like to make the SAE not just for interpretability, but it can be better served for the downstream task. And later, we also try to explore the diverse applications of SAE for improving large language model training. And currently, we are working on using the SAE to find the better data. Okay, to filter out the data, to filter out the high quality data for training. And there just already some papers saying that, okay, you can just, after doing this SAE-based filtering, only 3K data can give you better performance than the previously using 100K data set for doing the fine-tuning or post-training for certain tasks. And also, there's just another very hot topic about using SAE to do the safety control. Okay, so the story is that, okay, the SAE is mostly proposed by anaerobic, and anaerobic model, they have a very good safety control. They have if we have the safety benchmark, the Claude model will always have the best performance and it's way better than other models. So we suspected that inside the Anthropic company, inside the Claude model, perhaps they have already used the SAE for enhancing the safety and other related things in building their models. Okay, so that is all of the talk, and thank you for listening. And if you have any question, please ask now.
So for your slides, the mechanism of the sparsity. So there's a
you mean
encoder slides.
This one?
Oh yes, yes. So you are trying to penalize Xi.
Yeah.
But the width is a W, right? W ENC, W encoder, W decoder.
Yeah.
So I asked the question is so from statistical viewpoint, so there's also kind of a penalty or sparsity, but we are at the penalty on W rather than Xi. Okay.
Yeah,
have you tried on W or?
Yeah, I think that is from different perspective because like statistical thing, they just try to estimate something, and they're just to do the. I think that is more like complexity control for the weights. But here, it's just they have some like the explanation for sparse autoencoder is that this one is the dictionary. And this activation is the query for dictionary. And we just hope that for every data, we only pick as small as items in the dictionary. So we can only make, and in that way, we need to constrain the number of non-zero entries at Z, so which we can control how many items we need to get from the dictionary. So that I think that is kind of different from picking the sparsity control on the weights. So it's just making the sparsity control on the number of queries for the dictionary.
Okay.
Yeah. Because the goal is just to control the sparsity of Z. We just say we hope that for each data, for each input embedding, there are just only a few numbers of the items in the W decoder. W decoder is a dictionary of the key features. Okay. Only a few of them, they will be leveraged for representing this data.
Yeah, in terms of optimization, so the penalty of lambda, so actually we will go to, my understanding, it will control the W for encoder, W ENC, right?
Yeah, they will control both ENC and the decoder. Yeah.
Decoder is also control?
Because they are training together, so they must have like some like a coupled relationship.
Okay, okay. So okay. Oh yeah.
Yeah, I have a question. Just a high-level question. That have people tried to just directly design a neural network architecture with the sparse autoencoder inside, and then directly not naively train?
Yeah, that is a very nice question. I think currently there are no people working on that because this dimension is pretty high. Okay, so which means that dimension of W encoder and W decoder is pretty high. So if you train that simultaneously with other weights, that will cause a lot of memory cost. But in other way, so for this one, also last year, when OpenAI people, they just directly try to push the sparsity control over the number of neurons. They just say for each task, we only try to activate a few number of neurons. They are not trying to do that in the representation space. They are trying to do that in this architecture space because this one, they will not be involving much more trainable weights. But for this one, because W encoder and W decoder is super large. So for example, if we want to make this one to be super sparsity, if we want to handle more concept, this one could be million of order. The dimension could be million. And
Yeah,
they're just
thanks.
some like new work. So this one just for only one single layer. So they're just some new works. They try to build this SAE for multiple layers and say that perhaps some concept at the third layer, they have some connection with the features in the fifth layer. They try to build this called a transcoder. They try to combine these two SAE together by adding some links.
Yeah, thanks for the interesting talk. I just have a question about the input of the SAE. It will be a token or a sentence?
So they can be anything, but when doing that for large language model, we will only do this thing for the embedding of the token you want to predict, like the next token. So that's just one single token. But you can also do this kind of thing for the previous tokens. But that is kind of difficult because previous token, typically they are stored in the KV cache. It is very difficult to do the perturbation over the KV cache. So people just try to do the perturbation over the embeddings for the new incoming token.
So you also give an interpretability score. So I think I may miss something. So how do you define the interpretability score? So it's a little bit hard to define numerically or quantify it.
Yeah, that is still an open problem. They're just a different bunch of metrics for understanding the interpretability.
Yeah, I know.
So generally, the general way, just okay, if we find out, so we have already separated multiple features in the SAE. So we just deactivate one feature, and what we see, what happens about the output, to see whether the output, we compare the generated output before deactivating that particular feature and after deactivating that particular feature. And then we use a large language model to evaluate that, whether, okay, the concept has been removed by comparing these two bunch of output.
You suppress this node.
Yeah, so this is just one thing. The other one is also kind of similar to the steering. We activate something to see whether this concept can be added to this particular outcome. Then still using the large language model to do the evaluation. And I think that is kind of stupid because people really want to make this one to be a numerical value. So they just ask a large language model to give a score from 0 to 1 about that kind of thing. So that is, even though you can get a number called 0.9, but that one is not computed. That one is just directly assigned by large language model.
I'm also curious. So you have applied your SAE to the LLM, say the Q1, and so I'm just curious. So it is open, so you can.
It is open source.
It's open source.
For Q1, we trained by ourselves. We trained the Q1 by ourselves. For the Gamma, it's already open source. It's already have some open source model.
Oh, okay.
Yeah, but for Q1, there are also some open source model, but they're just different version of Q1 model. Sometimes their open source is not pretty good because this kind of research is mostly done by Google and Anthropic group, so they're mostly working on Gamma model.
Yeah. Okay, thanks. Any more questions from students?
Thank you, Professor Zhou, for your talk. I have such a question that if the in the second part, if the diffusion language model, if SAE works on diffusion language model, are you planning to apply it to diffusion model for multimodal language, multimodal?
Oh, yeah. You're saying whether SAE can also be applied for multimodal model, like image to text, text to image, something like that?
Yes.
Oh, there's already a lot of work doing that. But they are using a standard the large language model plus diffusion model, that kind of architecture. Like even for the standard text-to-image model using diffusion model in the continuous space, there are already very successful attempts at working on that, showing that, okay, adding this concept, you can just manipulate the generation of the image.
Oh, okay, thank you. So are they different very strong? Are they very different?
You mean difference between what?
Between diffusion language model and...
Yeah, they're very, very different. But so far, there are no work just try to study that for diffusion language model. But there's already some work working on the image, like the continuous conventional diffusion model, rather than diffusion language model. So I guess if in the future, using diffusion language model for doing the multimodal kind of task, perhaps like we can still using our pre-trained sparse autoencoder to working on that kind of stuff.
Okay. Thank you.
So it's already overrun. So I think you are all hungry. So let's thank Stephen again, and we can close that session.
Okay, thank you.